In this tutorial, you'll learn how to reproduce the copper example from the FactFlow paper in FactFlow. And so the copper example is primary production of copper, and actually FactFlow already comes packaged with the example files that reproduce each of the figures in the that are presented in the paper. So actually, I can show the specific ones I'm talking about here. So for example, figure 6 in the FactFlow paper, this one is the first figure of the copper example, and it shows the phase assemblage as a function of the quantity of O2 enriched air in the smelter. And so this is the first figure that we're going to try to reproduce here using FactFlow. And there's the corresponding file that's already included in FactFlow for this example, but we're going to try to reproduce it. And so the first thing we're going to do is click on New Project. So that's going to let us create a new project. And I can call this Copper for copper production. And double click the CST None. You can also click on File, Load CST here, but I'm going to double click on CST None in order to select a CST for our project. And the CST that we'll pick is the CU without e-waste CST. And so this is the CST that's already pre-made and comes with FactFlow for the copper example, so we can select that one. And so as you can see here, the CU CST has been selected. And now we can start dragging in some input nodes to define the inputs of our process. And so the first input, the one on top here, we're going to name it gas input. And before we enter some values, we just want to make sure that our units are fine. And so we're going to enter everything in Celsius, so let's select that. And for the quantity, we're going to want to enter everything in kilograms. And for the pressure, we're going to want to enter everything in bars. So that's just something that we've decided. And yeah. So for the temperature here, we're going to set 25 degrees for the gas input, and the pressure is going to be 2.6 bars here. The relative quantity, so we're gonna check mark this relative checkbox here, and what that's gonna allow us to do is instead of entering absolute values in the quantities in the stream view here, so instead of saying, for example, 5 kilograms of SI, we're able to put a percentage and then put a total quantity here. And so you'll see what I mean in a second here, but we're gonna say that this total quantity is going to be alpha, because for this first figure, like I showed you earlier, we're going to vary the amount of O2 enriched air, which is this specific input right here, and see the results as a function of this varied quantity. And so we're going to select, we're going to just type in alpha here, and in the alpha field on top, which is where we enter the range for the alpha, we're going to put 0 underscore 900 underscore 30. And so that means that we want to calculate all of the alpha values between 0 and 900 with steps of 30. And so that's going to be our total quantity. And for the rest, for the quantities here, we just want to enter percentages. And so what we want actually is O2 for the input that is inside of this node, because it's O2 enriched air. And we want this air to be 43.24% O2. For the rest, we want N2, and that's going to be 56.76% of N2. I use the search bar over here. I can click on clear to clear it, and then show active only. And so now you can see that we have our total is 100%, and our gas is composed of 43.24% O2 and 56.76% N2. Now we can move on to the next node. And so this is actually going to be our chalcopyrite input, so I can name this copper input. And for this node, the temperature is going to be 25 degrees, just like the other node, but the pressure is just going to be 1 bar. And this time we don't have to check relative, we can just enter the values directly. And so what we want actually is 1,000 kilograms of chalcopyrite, but it's going to be 8% H2O, so it's going to be hydrated. And so let's look up CuFeS2. We actually want 920 kilograms of chalcopyrite here because it's going to be 1,000 in total and 8% H2O. And I can put H2O and select and type in 80 here. So if I clear and show active only, so for this input node, we can see that we have 1,000 kilograms in total, with 92% being the chalcopyrite and 8% being the H2O, and we entered this in absolute values. Okay, now that we have our inputs, we're ready to move on to equilibrium reaction. And so I can drag in an equilibrium reactor here. and name it smelter because that's the part of the process that we're currently working on. And I can connect these inputs to this equilibrium reactor. So now all of the inputs, when I click run, the inputs will flow in the equilibrium reactor. And here we're just going to change the temperature of this equilibrium reaction to the temperature of the reaction. So that's going to be 1250 Celsius and the pressure to 2.6 bars. And so those are the kind of conditions in which we're going to have our equilibrium reaction. And now I have to decide what I want to do with this output. And so I'm actually going to split it. So this output, I'm going to connect it to a splitter, and I'm going to call this a phase splitter. And we're going to change the split type, which is essentially the mode of this splitter, to phase. And so that is going to allow us to split the output of this equilibrium reaction by phase. And we want to split it 3 ways. And so I'm going to increase the number of outputs here to 3 and click on apply. So that's going to create 3 output slots like this. And immediately I'm going to drag and drop 3 exit nodes in order to connect them to each of these output here. And then I'm going to click on the phase splitter and start selecting the settings for this phase splitter. And so in this particular case, I want to put 100% of the slag in the output 2, which is going to be this middle output over here. And so I'm going to put 100 for both of these rows on the output 2 column. And if I click on this exit node, I'm just going to change the name to slag output so it's clear that all of the slag from this equilibrium reaction is going to the slag output. For the mat, I'm going to put all of the mat, so 100% of the mat, in the output 3, and so all of the mat should go to this third output here. So I'm going to name this mat output accordingly. And for all of the rest of the outputs, so any phases, including the gas, the CU liquid that are generated, that are kind of that result from this equilibrium reaction here, I'm just going to leave it to everything is at 100% to output 1. And so this first output, I can call it other outputs. Now we basically set up our flow sheet, and if I click on run here, it's going to start calculating for each amount for the alpha. So you can see on the top right, the alpha is evolving and changing, and the alpha corresponds, like we saw earlier, to the total quantity of the air that we're injecting. And so we can tell if I react basically the chalcoyl pyrite with this variable quantity of air, how is that going to change the phase assemblage? Is basically what it is. And there's many ways to visualize the results in FactFlow. For example, one of these, well, I mean, all of these exit nodes, you can see if you click on them. On the right, you'll see a stream view where you can see the exit stream from this calculation. But what we're going to do in order to reproduce the figure that I showed you earlier is we're going to go on this smelter and double click it in order to open this results window. And we're going to go in outputs, and here at the bottom left you'll see an iteration spin box. And if I change this, it allows me to see the results for each iteration separately, so this is really handy for looking at the results for each iteration. And for example, if I go to iteration 15, this is an iteration where I have all of basically the phases that I'm interested in, so the gas, the mat, the slag, and the spinel. I want to plot these. And so I'm going to select all of these from the outputs. I selected this basically by just clicking on the first one and dragging it while holding my left button. And then I can right click and click on plot analysis, and it will generate this figure over here, which is the same as the figure 6 in the FactFlow paper. And so we have managed to reproduce the figure 6 that shows the phase assemblage as a function of the variable O2 enriched air that is presented in the FactFlow paper. And so now that we've completed basically the smelting part of the copper primary production flowsheet, let's move on now to the slag forming step. And so in order to do this, first we're going to adjust some things about the inputs for the smelting step. And so instead of, we're no longer going to be interested in varying the amount of air in this particular node. And so we're just going to set this to 680 kilograms, which was determined in the paper to be a good amount. And we're also going to add another node here, which is actually going to be SiO2, because we are going to use SiO2 as a fluxing agent for the smelting step as well. So I've added this node, and I can I can change the quantity here. So I'm going to select search up SiO2 and change this quantity to 100 kilograms. So this is going to be 100 kilograms of SiO2 in this particular node. And the temperature is going to be 25 degrees Celsius, and the pressure is going to be 1 bar for this input node. And so now we have everything suitable for the inputs to the smelter. And the next part, the slag forming step, we're going to start off with the matte output over here. So I'm going to delete this because this is no longer just going to be an exit node, and instead I'm going to put a reactor. And so one of the inputs to this reactor, I'm going to move this so that we can see better, is going to be the matte from this this first smelting reaction. But another input to this is going to be, there you go, there you go. Another input to this reaction is going to be the gas input. So we're going to put, once again, O2 enriched gas inside of this this second slag forming step. And the temperature is going to be 25 degrees Celsius, and the pressure is going to be 2.6 bars, once again, for the O2 enriched gas. And we're going to have, once again, the same kind of way of doing things. And so this is going to be a alpha value because we're going to vary the amount of O2 enriched air that's going inside here. And the alpha this time is we're going to vary from between 0 to 90 with steps of 10. So that's going to be 9 iterations. Sorry, actually maybe 10 iterations. And for the composition of the gas, it's going to be exactly the same thing as before. And so, yeah, we have relative checked here, so I can put percentages. So 43.24% of O2. And as for N2, we're going to put 56.76. And so that's going to be our composition for the gas. So I can click on show active only here, and it'll show a total of 100% with 43.24% of O2 and 56.76% of N2. And so that's going to be our input. We're going to vary it between 0 and 90 kilograms. And yeah, so this is going to be our second part of the slag forming step. The equilibrium reactor here, we're going to call it a slag forming, slag forming reactor, I guess. We're also going to make sure we're not forgetting to enter the correct temperature and pressure for this equilibrium reaction here. So this is going to be 1250 Celsius and 2.6 bars for this equilibrium reaction. And now we're ready to click run in order to start the simulation. And so it's going to go for 10 iterations, and we should have basically as a function of this varying air input from this specific node, we're going to be able to see the matte changing. And so we have, as expected, the matte as an output here, and we're able to kind of see, for example, if I just right click and click plot analysis, we can see the variation of the quantity of matte as a function of our alpha parameter. But what we're actually interested in more is the composition of the matte. So I'm going to select CUSNFE, plot analysis, and it's going to bring us to this kind of graph. It's going to produce this graph, but I'm going to click on relative here at the bottom right, so to get the kind of percentages of CUSNFE inside of the matte, and that's going to give us this graph, which is actually the 9A graph from the FactFlow paper. And so now we've reproduced these slag forming results as well. And I can close this, and hopefully, yes, we can move on to the next step, which is going to be copper making. So the first thing I'll do actually is, in order to make this a little bit prettier for the flow sheet, I'm going to rearrange kind of the nodes so that it's easier to visualize and see what's going on. And so this is kind of, I guess, what we can do. And we're actually going to add also a new input to this slag forming reactor here, which actually we can just call it a converter because this is in reality just a converter here. And I can put a new input and connect it. Oh, I need to actually change. So for this equilibrium reactor, we have 3 inputs. The first one being the gas input, the second one being this SiO2 input that we're going to put in this reactor, and finally matte output from the previous step. And so I can increase the number of inputs here to 3. So then I have 3 input slots, and then connect this SiO2 input. So I'm going to name this SiO2 input in the second slot of the reactor. So for SiO2, oh, I have an extra backslash here. For the SiO2 input, this is going to be 25 degrees Celsius and 1 bar for pressure. And we're just going to put SiO2 at a quantity of, so this is going to be quarts, 17 kilograms. And so this node will basically just be 17 kilograms of SiO2 that's injected inside of this this converter here. And now we're going to take this mat output, instead of just putting an exit node here, we're going to put a splitter. And so this splitter is going to be very similar in terms of the settings to the previous one that we had. And so it's going to be a phase splitter with 3 outputs like so. And the first, so the first output we're just going to set 100 to everything, so it's going to be the rest of the outputs. But for the mat, for example, we're going to put it on the third output. And for the middle outputs of the second output, we're going to put all of the slag. And like I said, the rest of all of the phases are going to be sent to the first output. So I can name this once again phase splitter and put some exit nodes here. So the first one is going to be, actually this is going to be mainly gas. So we're going to say gas output. For the second one, so the slag, this is going to be, let's just check something. Yeah, actually, also I have to enable the SiO2 that might be produced from this reaction. And so this SiO2 triatomite that I might be able, I'm going to just search it up. SiO2, yeah, so SiO2 triatomite S4 also, I'm going to set this to 100% to go in this middle output. And this is going to be SiO2 output, there you go. That's good. And for this third output, I'm going to make it react. And so it's going to react with something else, which is going to be my gas input. And once again, we're going to actually end up doing the same kind of thing that we did before, where we have a relative quantity of alpha, because we're going to vary the amount of gas here. And the composition of the gas is actually the same as the other composition, sorry, that we saw earlier. And so 43.24% of O2 and 56.76% of N2. That's going to be our two compositions. They sum up to 100 once again. And the temperature is going to be 25 degrees Celsius, and the pressure is going to be 2.6 for this input here. And we can name this once again a converter. And we can just set the temperature and pressure here to 1250 and 2.6, not 12.6, 2.6 bars for this equilibrium reaction. And finally, we're going to have our output, which is going to mainly be a mat output. And so now we have kind of this complete, this flow sheet that we see here. The first part being the smelter, the second part being slag form, and the last part being copper forming. And for the input of the gas here, we're going to change the quantity, vary the quantity between 20 kilograms and 240 kilograms with steps of 20. And before clicking run here, we just have to make sure that for this gas input that we previously had as alpha, we're setting it to a fixed value. And so in this case, I'm actually going to set it to a quantity of 60 kilograms. So I'm going to set 60 here. Because if not, we're going to vary both this gas input and this gas input at the same time, so we don't want that. And so this one we're just going to set to 60 kilograms and then run the calculation. Where did my, there you go. And once that's done, we're able to go on the mat output over here. And for example, if I just click on this converter for this copper making part, I can double click on this, open the results menu, and I can scroll through the iterations to find all of the results that I have. And for example, if I take iteration 4, I have CU liquid that's produced, gas, matte, spinel. If I select all of this and click on plot analysis, that gives us a figure that's very, very similar to figure 10a in the paper. So that's the one over here, this one. And so we successfully reproduced the copper making part of this copper primary production example as well. And that kind of concludes our tutorial on how to simulate the copper primary production in FactFlow. Thank you very much for watching.